Alrighty, so in this video, I'm just going to show you very quickly how we can use binary and integer variables in a Cplex program. Alright, so for this problem, it's just going to be very simple. We're going to have two binary variables, b1 and b2. And then maybe what we'll also have are some standard real continuous variables, x1 and x2. Now, they'll have to follow some set of constraints. And what we're going to do is we're going to put two of the binary variables together in one constraint. And then we can actually do funny stuff like we can include a binary and a continuous variable in the same constraint. It's perfectly allowed. The other things that we'll do is we'll say x2 has to be greater than 0. x1 can be anything. But we should also sort of define that they're both reals. And then we can say something like b1 and b2 are in 0 and 1. Okay, so what I'm going to do is flip over to Cplex and program all this stuff up. And we'll run it and show that this actually works. Okay, now moving over to Cplex, I created a new mod file, this one here, with bin dvars.mod, and I went ahead and added it to a run configuration. So the first thing we can do is we can introduce our decision variables. So maybe we have x1 and x2. And as you recall, for x2, we said that it has to be greater than or equal to 0, so we might as well say it's a float plus. Now for the binary variables, for some reason, Cplex in the Optimization Studio does not call them binary variables. I have no idea why. It actually calls them booleans. Again, so if you ever end up using Python to program Cplex or the interactive optimizer, the text-based one, then it actually calls those variables binary variables. But for some reason here, when we're typing in the name of the variables, these idea of floats and booleans, I guess that's sort of like a programming language type thing, right? Because in C++ and in Java, you talk about floats and booleans. While in optimization, we typically talk about binary variables. And so the reason why I think we actually use the word boolean here is for that reason. So again, we're going to have two boolean variables, b1 and b2. After that, we can go ahead and type in our cost function. So it was just 5 times b1 minus 3 times b2 minus 4 times x1 plus 5 times x2. Okay. At that point, we can now do our subject to constraints. And we have b1 plus b2 is equal to 1. I think we actually need equal. We then have b1 plus x1 is less than or equal to 5. The x2 is greater than 0 is handled by this constraint. And then automatically by defining the variables as booleans, we get our answer. Okay, so let's actually show that this works. So I'm going to run this run configuration. Again, make sure that it's set to default if you're just pressing the green button there. So let's go ahead and run it. Otherwise, you can just say run this and it will run the configuration. It's a little bit slow. And there you go. In this case, b1 is 0, b2 is 1, x1 is 5, and x2 is 2. So certainly, I can show you that this is working. So if I want to force b2 to be used, I could change this to minus 5,000. And you can solve this. And what will happen is b2 will become 0 and b1 will be used. And there we go. Okay, The other neat thing that's worth checking is to see whether we can actually write this as a quadratic program. So can we do b1 squared plus b2 up to? Right, so this is a quadratic. This is definitely positive semi-definite. So the idea of b1 squared plus b2 squared is the same thing as saying, let's say x transpose 1, 0, 0, 1, x, where x is equal to b1 and b2. Okay, so the identity matrix is positive semi-definite because I think the eigenvalues are 1. We have repeated eigenvalues of 1. So yeah. Okay, so let's actually test this out. I've never done this before, but we can see whether we can do a quadratic in terms of these binary variables. Ooh, it seems like it's doing something. So it actually worked, right? That's pretty neat. Another thing that might be worth checking out is if we can do a quadratic that mixes the binary variables with the continuous variables. So first we'll need to make a matrix that, or find a matrix that is convex. So let me tell you exactly what I mean by that. So let's see. So what I'm thinking is maybe we could do something like 10b1 squared plus, 2x1b1 plus x1 squared. I don't know. I think that might be convex. We'll check. And the idea is we have this cross term that includes both a float and a Boolean. So let's check if we can actually do that. I don't know what happened to octave. See what happened. Oh, there we go. Okay, so we're gonna have to make up a matrix. So let's do this. Give me 1 second. I'm just gonna pause real quick so I can clean up my desktop. Okay, so what I did is I'm just gonna make up a matrix that I know to be diagonal, and so this is the one that I'm gonna use. There's a little trick if you ever want to make a positive semi-definite matrix. You basically just take a vector and then you multiply it times itself. And I think that, I'm almost fairly certain that always gives you a positive semi-definite matrix. It's kind of like squaring a value always gives you a positive number, right? Same sort of idea. So as you can see here, my eigenvalues are 0, 0, 0, and 10. Or we could use, if we wanted to, we could try a different one. So we could say A is equal to 1, 3, 2, -5. Right? And I could make this my vector, so let's go, or my matrix. Let's see if that is positive semi-definite. And it certainly is now 0, 0, 39. So this involves a mixture of positive and negative, but just for simplicity, I'm gonna go with this guy here. Okay. So what I need to do is actually figure out what that multiplication is. So again, I'm gonna jump over. So effectively, what we're gonna now do is we're gonna test out this idea of we're gonna have the same minimization. Okay, so we're going to have a linear term, but then we're going to add in a quadratic term. Okay, and so we'll add in something like I'm just going to write this notationally, a ZQZ transpose. And what the Z is, the Z matrix, is going to be equal to a stacked version of all our variables. So maybe it has x1, x2, b1, b2. All right. And the Q matrix that we're going to use is the one that I generated in Octave. So this 1, 2, 2, 1, 2, 4, 4, and whatnot. So let's see if I can remember what that was. I think it was 2, 4, 4, 2. Let's see if that was what it was. Yeah, okay. So now what we need to do is we need to figure out what this matrix sort of sub-equation evaluates to algebraically. Okay, so let me try to find a quick way to do that because I don't really like the idea of multiplying all these vectors together. Probably going to make a big mistake. So give me one.
So Octave has a symbolic math tool. So if you look for OcSymPy, hopefully you can find it. And I'm going to give that a shot, and I'll show you why I'm doing that. So it's the symbolic package for GNU Octave.
It's a little bit complicated to install, so I'm just going to do this as an aside. But they definitely have at least, once you get Octave, you can download the symbolic file, you start up Octave, and then you go to your downloads folder. So in my case, here's my downloads folder, so I changed directories over to that. So you can just, click this up file and then pick whatever folder you want. So I'm in downloads. And then I want to make sure that I can find this file. So it seems like it is the symbolic win. So let's see if we can find that. And that's not it. It seems like it was called oct. So when I downloaded it, yeah, it's octsym, so slightly different name for some reason than the instructions here, which explains why here I looked up octsym and I find it here. So let's go ahead and try to follow the rest of these instructions. So we're gonna package install pkg install that file. Oh, I did not like that. Symbolic. I'm going to try the other one. Oh, this is the guy we want. Okay, let's try this. All right. Symbolic WinPy. Where did it go? Alright, so now it's installing a symbolic package. And what this is going to let us do is actually do some symbolic math in Octave. If you have MATLAB, this is a lot easier. Typically, most of you might already have this pre-installed. But here we're going to, because I don't have MATLAB running on my laptop, I'm going to go ahead and do this in Octave. So I'll unpause once it finishes installing. The next step that we're going to do is we're going to load this symbolic package. And I'll show you what why this is cool and what we can do with it if hopefully this works out.
Okay, so it seemed to have installed, but I had tried installing this earlier without much success. But it's
telling me to run news symbolic, so I'll give that a shot. And that seems to have done something that worked. And so, Sims. Okay, so I guess I need to do this next step, which is package load symbolic. PKG load symbolic. Okay. Yes. All right, so I'm going to call, let's see what's happening.
All right. So I just cut this because I figured out what was going on. If you saw the last part, I might have cut the video off. So what we're going to do is we're going to define some new variables. And these are going to be symbolic variables so that we can do symbolic math like we do in Wolfram Alpha. If you end up seeing something like you saw in the last video where it says like symbolic math 2.9.7 and then a colon, and you just see the cursor blinking, that just means it's loading the library for the first time. So just be a little bit patient. All right. So what I can then do is I'm going to define a matrix Z, or a vector Z with x1, x2, b1, and b2 in it. All right. So here goes my vector. I'm also going to define my matrix Q. So 1, 2, 2, 1. 2, 4, 4, 2, 2, 4, 4, 2, and then finally 1, 2, 2, 1. Okay, so this was the matrix that I had before. And now what I want to do is see what the algebraic equation is if I do x transpose times x. Oh, not x, sorry, this is z, because z is the vector that we defined. Right? And so this is really nice. It will actually hopefully work out all the math for me. And there we go. We got the math. It actually did all the multiplication, which is nice. And, you know, these are parentheses. I guess it's trying to do it a little bit simpler, but maybe we can do an expand or simplify. Let's see. Yeah, there we go. So this is essentially what the expansion looks like. So one thing we can do is we can just go ahead and copy this. Let's see if we can copy and paste this directly into our optimization. Okay. Oh yeah, there we go. That's really nice. Okay. The only weird thing are these overbars. I'm not quite sure what they represent. Oops. So we'll just get rid of these guys. Who knows? And again, the nice part with Octave, not everything actually needs to fit on the same line. So you could press return, and it knows to continue that line. So for example, I could break here just to make it a little bit more pretty, and break there. Okay, so what we should have is a problem that includes binary variables and real variables, continuous variables, and we actually have a quadratic program here. So let's see if Cplex can actually solve this. It's doing something, which is good news. Oh, and sure enough, it ends up solving. So, you know, this is a... Oh, and actually, let's change this back to 5, because maybe we'll get a better answer. So this is something that I didn't know, that we could actually mix continuous variables and binary variables as part of a quadratic program. Very surprising for me. So this goes to show how powerful Cplex is. Most solvers can't actually do this. Let's actually make one more change. So I'm going to change B2. Let's say we didn't want B2 to be a Boolean. What if we wanted it to be an integer? All right. The way we would do that is we would say define variable int B2. For this particular problem, in order to make this adjustment, we're going to do a few things. We'll say B1 plus B2 can be 5. Okay. That it has to sum up to 5. Okay. B1 is still a Boolean though, but B2 will be an integer. And now we'll see whether we can mix together. Here we have a continuous variable that could be negative infinity to infinity. X2 is a positive
continuous variable. So from 0 to infinity, b1 is a Boolean, and then b2 is an integer. So this gives you an idea of how we can mix all sorts of decision variables into a single program. All right, so let's see how...
Alright, sorry about that. It seems like somebody was sneaking into our candy drawer and my partner heard it. Okay, so again, the whole question is, can we solve this problem with
a whole mix of variables? And I suspect we can. Cplex is looking really, really powerful. So this is a huge step up from earlier versions of Cplex. And sure enough, what we see is b2 is allowed to be an integer. And it ends up solving to be 5. b1 is a Boolean variable, ends up being 0. x1 is a free-floating variable, ends up being -3. And x2 ends up being 0. So this is very, very nice. Again, we see how Cplex can integrate in continuous variables, Boolean variables, and integer variables. All right, so that's it for how do we go about programming Boolean, or what we call binary variables in Cplex. The next video that I'm going to do is going to explain how can we use these Boolean variables as indicator variables like we did in the lecture.